The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so let's try to discuss a bit how things relate to physics. Okay. So there's two main things I want to discuss. One of them is what curl says about force fields, and in particular, a nice consequence of that concerning gravitational attraction. Okay, so more about curl first. So we've seen if we have a velocity field, then we've seen that the curl measures the rotation effects. More precisely, curl V measures twice the angular velocity, or maybe I should say the angular velocity vector, because it also includes the axis of rotation. Okay, so I should say maybe for the rotation part of the motion. So, for example, just to remind you, I mean, we've seen this guy a couple of times, but if I give you a uniform rotation motion about the z-axis, so that's a vector field in which the trajectories are going to be circles centered on the z-axis, and our vector field is just going to be tangent to each of these circles. And if you look at it from above, then you'll have this rotation vector field that we've seen many times. So typically the velocity vector for this would be minus yi plus xj times maybe a number which represents how fast we're spinning, the angular velocity in radians per second. And then, if you compute the curl of this, you will end up with 2 omega times k. So now, the other kinds of vector fields we've seen physically are force fields. So the question is, what does the curl of a force field mean? What can we say about that? So the interpretation is a little bit less obvious, but let's try to get some idea of what it might be. Okay, so I want to remind you that if we have a solid in a force field, we can measure the torque of the force, the torque exerted by the force on the solid. So maybe first I should remind you about what torque is in space. So let's say that I have a piece of solid with a mass delta m, for example, and I have a force that's being exerted to it. Okay, so let's say that maybe my force might be F times delta m. If you think, for example, of a gravitational field, the gravitational force is actually the gravitational field times the mass. Okay, I mean, you can forget delta m if you don't like it. And let's say that the position vector, oops, should be aiming for the origin. The position vector r is here. And now let's say that maybe this guy is at the end of some arm or some metal thing, and I want to hold it in place. So the force is going to exert a torque relative to the origin that will try to measure how much I'm trying to swing this guy around the origin, and consequently how much effort I have to exert if I want to actually maintain it in its place by just holding it at the end of a stick here. Okay, so the torque is now a vector, which is just the cross product of the position vector with the force. And so what the torque measures, again, is the rotation effects of the force. And, you know, if you remember the principle that the derivative of velocity, which is acceleration, is force divided by mass, then the derivative of angular velocity should be angular acceleration, which is related to the torque per unit mass. And so let me just remind you, if I look at translation motions, you know, say I'm just looking at a point mass, so there's no rotation effects, then force divided by mass is acceleration, which is the derivative of velocity. And so what I'm claiming is that for rotation effects, we have a similar law, which maybe you've seen in 801. At least, well, it's one of the important things of solid mechanics, which is that the torque of a force divided by the moment of inertia. I'm cheating a little bit here, but if you can see how I'm cheating, then I'm sure you know how to state it correctly. And if you don't see how I'm cheating, then let's just ignore the details. Is angular acceleration. And angular acceleration is the derivative of angular velocity. Okay, so now if I think of curl as an operation which, from a velocity field, gives the angular velocity of its rotation effects, then you see that the curl of an acceleration field gives the angular acceleration in the rotation part of the acceleration effects. And therefore, the curl of a force field measures the torque per unit moment of inertia. So it measures how much torque this force field exerts on a small test solid placed in it. So if you have a small solid somewhere, the curl will just measure how much your solid starts spinning if you leave it in this force field. So in particular, a force field with no curl is a force field that does not generate any rotation motion. So that means, if you put an object in there that's completely immobile, and you leave it in that force field, well, of course, it might accelerate in some direction, but it won't start spinning. While if you put it in there spinning already in some direction, then, well, it should continue to spin in the same way. Of course, maybe there will be friction and things like that that will slow it down, but this force field is not responsible for it. Okay, so the cool consequence of this if a force field F derives from a potential. Okay, so that's what we've seen about conservative forces. So our main concern so far has been to say if we have a conservative force field, it means that the work of a force is the change in the energy, and in particular, we can't get energy for free out of it. And you know that the change in potential energy is going to be related to the change in kinetic energy, so that's, you have conservation of energy principles. Well, there's another thing that we know now, because if a force derives from a potential, then that means that its curl is 0. That's the criterion we've seen for a force to derive, for a vector field to derive from a potential. And if the curl is 0, then it means that actually this force does not generate any rotation effects. So, for example, if you try to understand where does the Earth come from, well, the Earth is spinning on itself as it goes around the sun. And you might wonder, where does that come from? Is that caused by gravitational attraction? And, well, the answer is no. Gravitational attraction in itself cannot cause the Earth to start spinning faster or slower. At least if you assume the Earth to be a solid, which actually is false. Okay? But still, it doesn't explain. I mean, basically, the reason why the Earth is spinning is because it was formed spinning. It didn't start spinning because of gravitational effects. And that's, a rather deep, purely mathematical consequence of understanding gravitation in this way. So it's quite spectacular that just, by abstract thinking, we got there. So actually, what's the truth? Well, the truth is actually the Earth, the Moon, and everything is actually slightly deformable. And so there's deformation, friction effects, tidal effects, and so on. And these actually cause rotations to get slightly synchronized with each other. So for example, if you want to explain why the Moon is always showing the same face to the Earth, so why the rotation of the Moon on itself is synchronized with its revolution around the Earth, that is actually explained by friction effects over time and the gravitational attraction of the Earth and the Moon. So there is something there. But if you took perfectly solid, perfectly rigid solid bodies, then gravitation would never cause any rotation effects. Okay? So of course that tells us that we don't know how to answer the question of why is the Earth spinning. And, well, that will be left for another physics class. I don't have a good answer to that. Okay. So that was kind of 801-ish. Let me now move forward to 802 stuff. So I wanted to tell you things about electric and magnetic fields. And in fact, something that's known as Maxwell's equations. So just a quick poll. If you have been taking, first of all, how many of you have been taking 802 or something like that? Okay, so that's not very many. So for most of you, this is a preview. If you've been taking 802, have you seen Maxwell's equations, at least part of them? Yeah, okay. So then I'm sure in that case you know better than me what I'm going to talk about because I'm not a physicist, but just in case. So Maxwell's equations govern how electric and magnetic fields behave, how they're caused by electric charges and their motions. And in particular, they explain a lot of things, such as how electrical devices work, but also how electromagnetic waves propagate. So in particular, that explains light and all sorts of waves. So it's thanks to them that your cell phone and your laptop and things like that work. But anyway, okay. So hopefully most of you know that the electric field is a vector field that basically tells you what kind of force will be exerted on a charged particle that you put in it. So if you have a particle carrying an electrical charge, then this vector field will tell you basically there will be an electric force, which is the charge times E, that will be exerted on that particle. And that's what's responsible, for example, for the flow of electrons when you have a voltage difference. Because classically, this guy is actually the gradient of a potential, and that potential is just electric voltage. The magnetic field is a little bit harder to think about if you've never seen it in physics, but it's what's causing for example, magnets to work. And, well, it's a force that's also expressed in terms of a vector field, usually called B. Some people call it H, but I'm going to use B. And that force tends to cause, if you have a moving charged particle, then that will cause it to deflect its trajectory and start rotating in the magnetic field. So what it does is not quite as easy as what the electric field does. Just to give you formulas, the force caused by the electric field is the charge times the electric field, and the force caused by the magnetic field is, well, I'm never sure about the sign. Is that the correct sign? Good. Okay. So now the question is, we need to understand how these fields themselves are caused by the charged particles that are placed in them. And so there's various laws in there that explain what's going on. So let me focus today on the electric field. So Maxwell's equations actually tell you about div and curl of these fields. So let's look at div and curl of the electric field. So the first equation is called the Gauss-Coulomb law. And it says that the divergence of the electric field is equal to, so this is just a physical constant. What it's equal to depends on what units you're using. And this guy, rho, well, it's not the same rho as in spherical coordinates because physicists somehow patented the use of that letter first. It's actually the electric charge density. So it's the amount of electric charge per unit volume. So what this tells you is that divergence of E is caused by the presence of electric charge. In particular, if you have an empty region of space, or a region where nothing has electrical charge, then E has divergence equal to 0. So now, that looks like a very abstract, strange equation. I mean, actually, it's a partial differential equation satisfied by the electric field E. And that's not very intuitive in any way. Okay, so what's actually more intuitive is what we get if we apply the divergence theorem to this equation. Okay, so if I think now about any closed surface, okay, and I want to think about the flux of the electric field out of that surface. So we haven't really thought about what the flux of a force field does, and I don't want to get into that because there's no very easy answer in general, but I'm going to explain soon how this can be useful sometimes. But so let's say that we want to find the flux of the electric field out of a closed surface. Then by the divergence theorem, that's equal to the triple integral over the region inside of div E dv, which is, by the equation, 1 over epsilon 0, that's this constant, times the triple integral of rho dv. But now if I integrate the charge density over the entire region, then what I will get is actually the total amount of electric charge inside the region. Okay, so that's the electric charge in D. So this one tells us in a more concrete way how electric charges placed in here influence the electric field around them. In particular, one application of that is if you want to study capacitors. So capacitors are these things that store energy by basically you have two plates, one that contains positive charge, the other negative charge, and then you have a voltage between these plates. And that can act, basically, that can provide electrical energy to power maybe an electrical circuit. And so, that's kind of, it's not really a battery because it doesn't store energy in large enough amounts for that. But for example, that's why, when you switch your favorite gadget off, it doesn't actually go off immediately, but somehow you see things dimming progressively. There's a capacitor in there. So if you want to understand how the voltage and the charge relate to each other, well, the voltage is obtained by integrating the electric field from one plate to the other plate. And the charges in the plates are what causes the electric field between the plates. So that's how you can get the relation between voltage and charge in these guys. That's an example of application of that. Okay, now, of course, if you haven't seen any of this, then maybe it's a little bit esoteric, but that will tell you, part of what you will see in 802. Okay. Questions? I see some confused faces. Okay, well, don't worry. It will make sense someday. So the next one I want to tell you about is Faraday's law. So in case you're confused, by the way, I should say Maxwell's equations. So there's 4 equations in the set of Maxwell's equations, and most of them don't carry Maxwell's name. I mean, that's a quirky feature of them. But so that one tells you about the curl of the electric field. So now, depending on your knowledge, you might start telling me, well, the curl of the electric field has to be 0 because it derives from, actually, it's the gradient of the electric potential. I told you this stuff about voltage. Well, that doesn't account for the fact that sometimes you can create voltage out of nowhere using magnetic fields. And in fact, you have a failure of conservativity of the electric force if you have a magnetic field. So what this one says is actually the curl of E is not 0, but rather it's the derivative of the magnetic field with respect to time. Okay, so more precisely, it tells you that what you might have learned about electric fields deriving from electric potential becomes false if you have a variable magnetic field. And just to tell you, that's again a strange partial differential equation relating these 2 vector fields. So to make sense of it, one should use Stokes' theorem. Okay, so if we apply Stokes' theorem to compute the work done by the electric field around a closed curve. So that means, you have a wire in there, and you want to find the voltage along the wire. So now there's a strange thing, because classically, you would say, well, if I just have a wire with nothing in it, there's no voltage on it. Well, small change in plans, if you actually have a varying magnetic field that passes through that wire, then that will actually generate voltage in it. And that's how a transformer works. So a transformer, when you plug your laptop into the wall socket, you don't actually feed it directly 110 volts or 120 volts or whatever. There's a transformer in there. And what the transformer does is it takes some input voltage and it passes that through basically a loop of wire. Okay? Not much seems to be happening. But now you have another loop of wire that is intertwined with it. And somehow the magnetic field generated by, so it has to be alternating current. The alternating current varies over time in the first wire that generates a magnetic field that varies over time. So that causes dB by dt, and that causes curl of the electric field. And the curl of the electric field will generate voltage between these 2 guys. And that's how a transformer works. It uses Stokes' theorem. Okay? So more precisely, how do we find the voltage between these 2 points? Well, let's close the loop, and let's try to figure out the voltage inside this loop. So to find the voltage along a closed curve placed in a varying magnetic field, so we have to do the line integral along a closed curve of the electric field. And you should think of this as the voltage generated in this circuit. That will be the flux through this surface bounded by the curve of curl E dot ds. That's what Stokes' theorem says. And now if you combine with Faraday's law, you end up with the flux through S of minus dB dt. And of course, you could take, if your loop doesn't move over time. So I mean, actually, there's a different story if you start somehow taking your wire and somehow moving it inside the field. But if you don't do that, if it's the field that's moving, then you just can take the d by dt outside. But let's not bother. Okay, so again, what this equation tells you is that if magnetic field changes over time, then it creates, just out of nowhere, an electric field. And that electric field can be used to power things. Okay. So I don't really claim that I've given you enough details to understand how they work, but basically, these equations are at the heart of understanding how things like capacitors and transformers work. And they also explain a lot of other things, but I will leave that to your physics teachers. Just for completeness, let me just give you the last two equations in that. I'm not even going to try to explain them too much. So one of them says that the divergence of the magnetic field is 0, which somehow is fortunate because otherwise you would run into trouble trying to understand surface independence when you apply Stokes' theorem in here. And the last one tells you how the curl of the magnetic field is caused by motion of charged particles. So in fact, it says that the curl of B is given by this kind of formula, where J is what's called the vector current density. So it measures the flow of electrically charged particles. Okay, so you get this guy when you start taking charged particles, like electrons maybe, and moving them around. And of course, that's actually part of how transformers work, because I've told you, running the AC through the first loop generates a magnetic field. Well, how does it do that? It's thanks to this equation. If you have a current passing in the loop, that causes a magnetic field, and in turn, through the other equation, that causes an electric field, which in turn causes a current. So it's all somehow intertwined in a very intricate way, and it's really remarkable how well that works in practice. Okay, so I think that's basically all I wanted to say about 802. I don't want to, put your physics teachers out of a job. So if you haven't seen any of this before, I understand that this is probably not detailed enough to be really understandable. But hopefully it will make you a bit curious about that and prompt you to, take that class someday and maybe even remember how it relates to 1802.